All right, deterministic and probabilistic sensitivity analyses. And so in this class, we've already talked a lot about how these models are inherently wrong, that there's a lot of assumptions that can go into these models. And now we have to go about evaluating those assumptions. How can we evaluate the variability around our parameters? So, I mean, think about it like a randomized clinical trial. If you were to run this trial, you're going to get a treatment effect, like a point estimate. And nobody stops there. In statistics, we always then go on to evaluate a confidence interval around that effect estimate. We want to do the same thing here. All the work we've done so far has been about identifying or calculating a point estimate ICER. Now we have to explore the uncertainty. Now we got to start to calculate a range around that ICER. So the main type of uncertainty or assumption that we're going to talk about in this class is parameter uncertainty. So this is our bread and butter. This is what we're doing when we say one-way sensitivity analyses or probabilistic sensitivity analyses, which is what we're doing today. But I do want to point out that there are other types of uncertainty, and this isn't even a comprehensive list. I'm just going to briefly go over these other types of uncertainty. They often aren't evaluated in models, but they're important to recognize. And I think it's important to help us just like frame the type of uncertainty as we're talking about these models. Stochastic uncertainty refers to random variability between patients that's not based on any sort of clinical characteristic that we can identify. So imagine you have two patients who you see that have basically identical clinical characteristics, same demographics. There's not really any reason that you would expect them to perform differently, and yet they experience very different outcomes. That's an example of stochastic uncertainty. It's the randomness of life. Heterogeneity, on the other hand, refers to differences that patients might experience because of an important clinical difference. So if you think about a randomized clinical trial, imagine the subgroup analyses that people do at the end where they're testing whether different subgroups experience different treatment effects. That's heterogeneity. And then structural uncertainty is a broad term that can refer to the way we build these models and the assumptions that go into building the models. So as we talk about the branches we've mentioned before that when we build a model, we have to be explicit about everything that can happen, and anything that we don't draw or put into the model, we're assuming can't happen. Now, there's no perfect way to build these models, and we kind of make it up as we go. And so those assumptions, those refer to the structural uncertainty. But these first three often aren't evaluated in cost-effectiveness models. They can be important things to evaluate. I want to point them out, but the thing that gets evaluated every single time, every single paper, is parameter uncertainty, and that's what we're going to talk about today. So I'm going to skip through this because we just talked about what these other types of uncertainty mean, but it brings us to parameter uncertainty. So this is uncertainty in the estimates that we put into the model. So the costs, the probabilities, the utility values, etc. And then it can be either deterministic or probabilistic. And we've mentioned these terms at the beginning of the class, I believe, and they're fancy ways of saying whether there's randomness or not. So a deterministic sensitivity analysis, we're assuming no randomness. We're setting the parameter. There's not probability. There's not chance involved. And whereas probabilistic sensitivity or probabilistic analyses, there is randomness, there is chance. We're rolling the dice and seeing what happens. So broadly speaking, these are the steps involved with doing these analyses. So the first step is to identify the uncertain parameters. In reality, basically every parameter is uncertain. There's very few times where you have a parameter where you're like, yes, I know this parameter, it's locked in, it is certain. And think about, again, I'm going to go back to the idea of a clinical trial. So somebody is going to evaluate and get a point estimate, and then they're going to calculate that confidence interval because they're not confident in that point estimate. There's some probability, some chance that their mean estimate is wrong, or that it's going to vary if we evaluate it in another population. So there's always just some variability or some uncertainty that goes into these estimates. Maybe an example of a time when there wouldn't be is if, let's say, you're doing an analysis from the perspective of the University of Utah healthcare system, and you're evaluating the cost of a medication, and you actually have a contract in hand and you know how much you're paying for that medication. Well, now we don't have to evaluate uncertainty there. We know what it costs. But that's very rare. It almost never happens where we don't have some uncertainty around a parameter. And then we're going to, the second step is we're going to do a deterministic analysis. And then the third step is we're going to do a probabilistic analysis. The way we do deterministic analyses is the most common is called a one-way sensitivity analysis. And this is where we're going to vary one parameter at a time in a model while holding everything else constant. So let's go back to our HIV example that we used last week. So this is the hypothetical analysis of these two made-up drugs, Alphamax and Betacom. And here what this table is showing us is the parameters that we use in our model. So we have the base case, or actually I may think I highlighted them. Yep. So let's do it like this. So we have our two drugs, Alphamax and Betacom. The base case is the mean estimate. This is what we assume is our best guess for what this parameter really is. So you have the model parameters over here. So let's look, for example, at the probability of being adherent. With Alphamax, the probability of adherence is 50% as the base case, and with Betacom, the probability of adherence was 70%. But then we have a low estimate and a high estimate. And our goal with coming up with low and high estimates is determining what is a plausible range in the real world. So we don't want to artificially create these. A lot of the best way to do this is if you have a publication with a 95% confidence interval, we're going to use that 95% confidence interval as our low and our high estimate. So the way that this analysis works is we're going to go one parameter at a time, and even in one medication or one strategy at a time. So in this case, we're looking at the probability of adherence, and we're only looking at the probability of adherence with Alphamax. And then we're going to hold everything else constant. So everything else gets held at its base case value, and we're going to vary the probability of Alphamax from its high to its low and see how the ICER changes. So this is just this table is just showing you an example of doing that. So to orient you, we have the value or the parameter that's going to go into the model. In this case, it's the probability of being adherent to Alphamax. So we're going to start with a probability of 0.3. This is there's two rows because we're looking at both of the different strategies. So this is the Alphamax strategy and the Betacom strategy. Now notice we're not actually varying anything with the Betacom strategy. It's still just looking at the probability of being adherent to Alphamax. That's the only thing we're changing. And then we record the cost, the incremental cost, the effectiveness, the incremental effectiveness, and come up with an ICER. And then we're going to do it again. Now we're going to slightly increase the probability of being adherent to Alphamax. Now we're at 0.375. And you see we get a new ICER when we use that value. And so on and so forth until we get to the high range. So we varied it from 0.3 to 0.6. We record our ICERs and we get a range of ICERs that could potentially happen as we move across this range of probabilities of being adherent to Alphamax. Now, what you'll notice is, or one question you might have is, well, why did we do this 5 different times? Why didn't we just do the high and the low value, 0.3, 0.6? And the reason is because this example, we have an almost linear line where the low value resulted in a low ICER, and then the high value resulted in a high ICER. But we don't always have this relationship depending on how your model is built and run. There are times when the relationship between the ICER or the parameter and the ICER is not linear. So imagine you had a relationship that looked like this, where if you use the low value, you have a pretty low ICER, and if you use the high value, you also have a high ICER, but somewhere in between, the ICER goes up. Now, I don't have a great example of this off the top of my head, but I do want to point out that these sort of relationships between parameters and the ICER can occur. And in this case, we still want to know what's the high and low ICER that can occur. So we would say the ICER can vary from here to here. In this case, it's from high to low, here to here. And so we often divide up the take the range and divide it into some equal amount. Here we used 5 different times. I think it's pretty common to do this 10 different times. It doesn't really matter as long as you're having enough. You're doing it enough times that you can start to see the relationship between the two parameters, or the parameter and the ICER, and then we're going to record the high and the low as the range that this parameter can affect the ICER. I hope that makes sense. We can talk about it in class if that was confusing. So this is just graphing that. So we have the probability of being adherent to alpha max, and then the ICERs that resulted. And we typically represent these analyses, these one-way sensitivity analyses, with something called a tornado diagram. So let me just pull up a tornado diagram and we can talk about it. So the first thing I want to point out is that the axis down here is the ICER. It's not always the ICER. In this case, we are using it as the ICER. People can use other types. You can use like net monetary benefit. You can use other variables, but most commonly it's the ICER. Now we have this dashed line right here, and this dashed line represents the base case analysis. And then what we're doing now is we're going parameter by parameter and rank ordering the parameters based on the width of how much they influence the ICER. So, and then like right here, if you look at our what do you call this? The key or legend, the green bar represents the probability of having a CD4 count greater than 200 with Betacom. So our range was 0.75 to 0.95. And as we varied this estimate or this parameter in the model, we came up with a low and a high ICER, and then we graph it. And then we say, well, what was the next parameter that had the most impact on the model? And then we just draw it down. Now, here's how I use these graphs, or how I kind of would encourage you to use these graphs. The first is that by rank ordering the parameters, we're actually able to see which parameters have the most influence or most impact on our model. And that's important because now we can come in and say, well, how confident are we in this probability of CD4 count? Do we have really good data around it? It really influences our model. And we can start to kind of make some guesses about how much we think this really matters. The second way I use these is I love to come in and like look at my willingness to pay and ask the question of, do any of the parameters or all of the parameters qualitatively influence the way I'm going to think about this decision? So let's just use for an example a willingness to pay of 50,000 per quali, and we'll say, and then we'll also use 150,000 per quali, and we'll say that anything below 50,000 is considered high value care. Like we're like, man, that's super cost effective. Anything above 150, we're going to say is low value care. We don't want to pay for low value care. We want to pay for high value care. And then anything in the middle is going to be considered medium or moderate value care. Well, if we look at these parameters, what you see is yes, there is some variability here, but in no case, except for maybe the probability of CD4, and then it's just a tiny little bit. At no case do we actually qualitatively move into a different interpretation of the results. So we would say with some confidence, like this is medium value care. And no, as we looked at a plausible range for these parameters, at no point did it become high or low value care. We can do two-way sensitivity analyses. So two-way sensitivity analyses are exactly the same as one-way, but we're going to vary two parameters at the same time. So it's exactly what it sounds like. So let's look at an example here. So we have the cost of a 1-month drug supply of drug. And if we vary both the alpha max and the Betacom at the same time, we can see how that influences results. But we're going to hold everything else constant. This is still a deterministic sensitivity analysis. This is a common type of graph that would come out of a two-way sensitivity analysis. So to orient you, we have the cost of beta com on this axis, and we have the cost of alpha max on this axis. Here we actually have to set a willingness to pay value. And the reason being is because we want to know at any 2 points, what's the preferred option. And we only know if an option is preferred if it's above or below our willingness to pay, if the ICER is above or below our willingness to pay value. So for example, let's assume that the cost of Betacom is $1,500 and the cost of Alpha Max is $600. Well, we can just draw a line to that spot and say, if we were to use those two values, what is the ICER? And then which drug does it favor? In this case, it favors Alpha Max, because all the area in blue favors Alpha Max, all the area in this pinkish red favors Betacom. This should make sense as the cost of Alpha Max goes up, and the cost of, as the cost of Betacom goes up and the cost of Alpha Max goes down, Alpha Max tends to be preferred. And conversely, as the cost of Alpha Max goes up and the cost of Betacom comes down, Betacom becomes preferred at a willingness to pay of $75,000. So the problem with two-way, you don't have to do it this way. There are other ways to graphically show two-way sensitivity analyses, but if you want to use this style, this approach, you have to set a willingness to pay. And that brings us to probabilistic sensitivity analysis, which I think are really fun. Now we're looking at joint uncertainty across all the variables in the model. And I think these are some of the most important analyses that we do in cost effectiveness when we publish these papers. So we're going to vary every parameter at the same time. And now we're going to allow chance. We're going to, we're rolling dice, we're flipping coins, and we're going to see what happens when we do that. And it allows us to start to get an estimate of the uncertainty around the ICER. Now, one thing I'll point out is that we can't actually calculate 95% confidence intervals. And that's because it has to do with math. So the ICER is a ratio, and we start to, it comes back to, if you remember from like high school math, like you can have, with ratios, you have like asymptotes at 0 and you get some funny looking things. So we don't actually calculate 95% confidence intervals in the true sense of biostatistics, but what we can do is we can start to calculate things that we'll call like a 95% uncertainty interval. That it doesn't really matter. You don't need to know the difference. I don't really fully understand the difference all the time, but I just been pointing that out. So here's what we do with a probabilistic sensitivity analysis. So we're going to start with the parameter, the probability of being adherent to alpha max, okay? And this is the exact same as before. We have a base case here. We have our low and our high estimate. But what we want to know, or what this fails to like show, is that the likelihood that the estimate of the probability of being adherent, the true estimate in our population, is closer to 50% and less likely to be at the low and high extremes. So we're going to create a distribution of likelihood around that parameter. So here we have a graph of a distribution. We have the probability of an estimate or a parameter or value occurring on the y-axis, and then we have the parameter of interest on the x-axis, which ranges, because this is a probability, it's constrained between 0 and 1 or 0 and 100%. And you can see that if we build this distribution, the most likely values are close to 0.5. And then as you start to get beyond, or more toward the extremes, the likelihood goes to almost 0. So in this case, we used a beta distribution. We have to actually, we have to build these distributions. So we choose the shape of the distribution that we're going to use in our model. And then we also provide it the parameters to calculate the distribution. So here again, now we have the probability of adherence to Betacom. And Betacom, you see, has a little bit different variables, and maybe we have a quite different shaped distribution here. We're still using a beta, but the beta, I'll just say the beta common distribution looks a lot different than the alpha max distribution, and that's because we created a different distribution. So how do you actually go about creating these distributions? There's a lot of ways to do it. There's dozens of different types of distributions. I'm just going to point out some of the most common ones that we use. Anytime we have a proportion or a probability, we have to constrain it between 0 and 1. The most common distribution we use is beta. Costs are commonly used either as a gamma distribution or even a normal distribution. So a normal distribution, it looks like a bell curve. So we can have distributions that are really skewed in one way or the other. We can have distributions that look like bell curves. We can there's a lot of different ways to do these. There's also, you can use log normal. Uniform just says the distribution is the same. It's almost like using when we talked about how the low end's less common than the high end in a normal distribution or uniform distribution. It's all the same. Triangular distributions are only seen in cost effectiveness now, or these kind of not cost effective, but this is in these models. So we say this is the low value, this is the high value, and this is the most common, and it's a really easy distribution to create. The problem with uniform distributions and triangular distributions is they don't occur in the real world. So they're kind of inherently wrong. People use them when they don't have enough data and they're trying to make something up, and they're just easy to program and implement. For utility values, we often use beta or gamma. And then when we have treatment effect estimates, so relative risk, hazard ratios, odds ratios, etc., we typically are using log normal distributions. All right, so this is some of the results that we can get from a probabilistic sensitivity analysis. So we have our incremental costs, so the cost of alpha max minus the cost of beta com, beta com minus alpha max, and then the incremental effectiveness here. And what we do to create this scatter plot is the model is going to take all of our distributions. So I'm going to draw a random distribution for one of our parameters. It's going to randomly pick a value based on the likelihood of that, or based on the distribution. It's going to randomly pick a value, and then it's going to do it for all of the different parameters we have in the model. It's going to pick a value, it's going to pick a value for every parameter. It's going to run the model, and then it's going to record the result. So the incremental cost, the incremental effects, and then it's going to do it again. It's going to pick a new value, and these values are randomly picked based on the distributions. It's going to record the new result. It's going to do it again and again and again, and we often do it 1,000 times or more. And we start to get this scatter plot of the ICER, of the cost, the incremental cost, and the incremental effects, which can then be used to calculate the ICER. And remember, we can draw a willingness to pay as a line. It's like, y equals mx plus b, if you remember your high school algebra. And so as we draw this line, so our willingness to pay here of $50,000 per opportunistic infection avoided, and we can say that anything below the line is going to be cost effective, and anything above the line is not going to be cost effective at that willingness to pay. And you can see if our willingness to pay is $50,000, this is probably not a cost-effective strategy. There's only a couple dots below the line. But if our willingness to pay goes up, now we have a willingness to pay of $100,000, it starts to be closer to 50-50. There's a lot of dots below the line. And saying, we can just keep going. Willingness to pay of $150. And we often use scatter plots to create this graph right here, the cost effectiveness acceptability curve. And I love this graph. I think this is a graph that I always encourage people to put into their papers. What we have here on the y-axis is the percent iterations that were considered cost effective. And if you remember, what we just said was to be considered cost effective, it had to fall below that line. So in other words, it's what's the probability that this is cost effective given your willingness to pay. So as our willingness to pay goes up, so does the probability that we consider this a cost effective intervention. So let's look at the graph we just drew, or the graph we just had in the graph we're trying to draw. So here we have our incremental cost effectiveness plane again, or a scatter plot. We have our willingness to pay line, and so at a willingness to pay of $50,000, that's this line, we can add up how many dots fell below that line and say, it's basically 0%. So 5 out of 1,000 fell below the line when it was at $50,000 as the willingness to pay. But if we increase the line, now you see we're closer to 50-50 by the time we get to 100,000. And by the time we get to 150,000, we're, close to maybe 90% probability of being cost effective. That's a PSA. That's a probabilistic sensitivity analysis. It does take some time and effort to actually build the distributions and to make sure you're getting your distributions right. And then we run the model. The model takes a lot more time to run because it's a lot more computationally intensive. But yeah, that's it. That's parameter uncertainty and how we evaluate parameter uncertainty using both deterministic sensitivity analyses and probabilistic sensitivity analyses. We didn't talk that much about other types of uncertainty. So again, heterogeneity, stochastic uncertainty, structural uncertainty. If you go look at like the ISPOR Good Modeling Practice Guidelines, they talk about other types of uncertainty as well. Those are less commonly addressed in papers and publications. Not that they're not important, but parameter uncertainty always has to be done. I hope this was helpful. Please reach out if you have any questions. Otherwise, we'll talk on Tuesday.